Welcome to this fourth lecture video for Physics 4B. In this lecture, we fill in some gaps that exist in our textbook, OpenStax University Physics Volume 2, by covering a few examples of heat engine cycles in some detail, utilizing the first law of thermodynamics we introduced in the last lecture. We will first talk about the difference in emphasis as we cover thermodynamics in this physics class, which is why we spend this extra time analyzing heat engine cycles not analyzed in detail in our textbook. We first look at a couple toy models in order to outline our general, almost mechanical procedure that applies to all thermodynamic processes. Once we have practiced the procedure with the toy models, then we cover the idealized Carnot heat engine cycle. And because no real-world engine actually operates in a cycle that could even be idealized as a Carnot cycle, we give three realistic examples of heat engine cycles. Otto cycle, which models most internal combustion engines in automobiles. Diesel cycle, which models diesel engines. And Stirling cycle, not widely used practically, but which you can see as a lecture demo of a heat engine running on an external heat source. We then summarize these four heat engine cycles, in particular calculating their efficiency, work done divided by heat input, under comparable conditions. Please note that so far we have neither introduced nor utilized the concept of entropy or the second law of thermodynamics. We will do that in our next lecture. I first want you to cover as much of heat engine cycles as we can without needing to introduce the second law of thermodynamics, because there's quite a lot we can talk about and calculate using only what we already know from mechanics. Let me get started with our first agenda item, which is what I described as some lecture on heat engine cycles. I guess this is what I wanted to start out with. It's a philosophical question of why do we cover thermodynamics? In physics specifically, I mean, because thermodynamics, if you've taken chemistry, you've covered it. So if you're looking at like things in chapter 2, ideal gas law, if you've taken chemistry, you have seen it in chemistry, and things like heat capacity and even maybe distribution of molecular speeds. All these are stuff covered in chemistry, and in chemistry you actually go into more depth. So the natural question is, why do we cover this in physics? And there's a purpose to it rather than just repeating it. And you can kind of see this almost existential question on why do we cover thermodynamics in lower division physics in sort of a variation you see between different textbooks and different schools covering thermodynamics at different places. When you are looking at things like mechanics, modern physics, and electromagnetism, those are standard. Like every school starts out with the mechanics, Newtonian mechanics that you have seen in Physics 4A. Every school covers electromagnetism in the second semester. And almost every school covers modern physics, special relativity, quantum mechanics in the third semester of calculus-based physics. And thermodynamics is the one topic that you will see covered in different semesters. It's possible to cover it in the first semester. You can somehow fit that in, and it's also possible to cover it in the third semester, maybe just before quantum mechanics. You can actually almost see that in how we covered, I think, some of the chapter 1 material. Because in chapter 1, we talked about, the textbook covers Stefan Boltzmann law in I guess under mechanisms of heat transfer, and we almost do nothing with it. And if we are doing quantum mechanics, then it leads naturally into black body radiation and Planck law. And so it's a good question. Why do we um, both why do we cover thermodynamics and where does it fit into lower division physics curriculum? And I do believe it should be covered, and covered in a way that it's distinguishable from how it's covered in chemistry, because this is the one topic where there's quite a deal of overlap between what's covered in chemistry and what's covered in physics. And really the place where you start to see that distinction, I think, is in chapter 3, when we start to talk about mechanical work, because that's the kind of thing that we physicists care about. So when you start to see the description of work done by a system, and we use the word system, and almost always in this lower division physics class, whenever we are talking about a system, we are actually talking about a system of gas, ideal gas. So we describe work done by a system in terms of the pressure of the gas and the change in the volume of the gas. So when we start to talk about mechanical work done by thermodynamic system, then that's where you start to see something that you would only see in physics class. And what we are covering in this week, I'm hoping to fill in a bit of a gap that I see in our textbook, and it might be because I'm kind of remembering what I saw in my own physics class when I was an undergraduate student and taking lower division physics. And when I look for those elements in our text, this is probably just about the one thing that I see missing in OpenStax University Physics. Let me sort of highlight what I see missing. So, we talk about work done by a thermodynamic system, and your textbook talks about different thermodynamic processes. And actually, I do like this coverage of quasi-static and non-quasi-static processes, because it kind of explains that every process you see described by a line in a PV diagram is quasi-static. It has to be by definition, or by kind of implication of drawing a line on a diagram. And it talks about isothermal process, and at the end it summarizes all 4 named processes: isothermal, adiabatic, isobaric, isochoric. It even uses the right word. It doesn't use isovolumetric, which I only bring that up to say that I'll never use that particular word. And it covers, of course, it covers first law of thermodynamics, which relates the mechanical work done. So I think first law is the kind of thing that you also see in a chemistry class, but the emphasis is probably different. So when we talk about work done, we are almost exclusively talking about mechanical work done, force applied over a distance, from which we get pressure times change in volume, and how that work done relates to heat transfer and change in internal energy. And all of this is relevant in talking about really the one thing that can only be covered in a physics class, which is the question of how you reverse something that you are used to seeing in the other direction. In physics 4A, for example, you are used to seeing work going in this direction, from where you have mechanical work, and as you are doing the mechanical work on some object, through friction, that mechanical work turns into heat. So, in the context of physics 4A, it's lost energy. And what you never see in physics 4A is a process going in the other direction, where you start out with some heat energy, thermal energy, and somehow turn that thermal energy into mechanical work. So that's what we are getting at in this first 4 weeks of Physics 4B. And the first law of thermodynamics, how kind of provides a starting place of how that might be possible, that, you know, from the consideration of conservation of energy, that, you know, if you have a heat transfer, if somehow that can be turned into mechanical work. At least the first law of thermodynamics states that, you know, that can be done. It's not inconsistent with the laws of nature. Now, this is the gap I see in your textbook, and the device we use to do that is a heat engine. And you know, you can kind of see hints of that in thermodynamic process and in the discussion of work done by a system, how as a gas expands, it's doing work, you know, all this diagram, and connecting all that and putting it into almost a practical device is the heat engine. And now when you go to chapter 4 and look under heat engines, you see almost what you would see for a conceptual physics class. There's this nice but somewhat schematic representation of what a heat engine does, you know, the kind of flow of energy, heat flow in, work out, heat flow out, and it's very schematic. And it feels like there should be more in the rest of the section, and there isn't. There is some detail covered for Carnot cycle, but your textbook doesn't quite cover any other heat engine cycles, and I think that is a real gap, because the Carnot cycle by its nature is a kind of theoretical process. If it were an engine cycle, it's a very impractical engine cycle. So I wanted to show you what I remember seeing in the textbook that I studied physics out of. So let me join with my other account, unshare my screen, and spotlight that. Sorry, I was trying to find this online, and this is the reason we use OER, which is that it's a lot easier to find online resource that's not encumbered by copyright. So I have this hard copy of the textbook that it's the same version as what I used when I was studying lower division physics. Let me stop sharing here and spotlight the video from my other account. So this is you know, there are many university physics textbook. This is University Physics by Young and Friedman. This version is, you know, almost 2 decades. Well, not out of date quite, but it came out about 2 decades ago. And this is the section that I remember from that textbook. And because I remember practical internal combustion engine being covered in quite a bit of detail. So this is the Otto cycle, which is probably the majority of real world heat engines you would see. This is automobile engine. It's the defining feature is that there's a spark plug that ignites the engine at the correct point in the cycle. And if you and this section also talks about, so this is the diagram for Otto cycle, a version of which you see in my other recorded videos. And it also covers the diesel cycle down here. And this is the diagram of the diesel cycle. So that's what I thought was missing looking at your textbook, that where's the detailed discussion of heat engines. And let me reshare my screen. Now, your textbook does have references to Otto cycle and diesel cycle, and it occurs in a form of textbook questions. They listed as a challenge problem. So problem 88 in your textbook covers, in some sense, Otto cycle, and the and 89 covers diesel cycle. And I think it's because so much of what we do with the PV diagram can seem like just a mathematical exercise. I think it's useful to be reminded of what practical, real world thing these are connected to, and that's why we are basically taking out an entire week of our 4-week schedule for thermodynamics to do an in-depth study of heat engine cycles. Hi, in this video, we will develop a systematic approach to analyzing heat engine cycles using PV diagrams. We are going to use a simple cycle so that we can illustrate the approach rather than trying to calculate for a realistic heat engine cycle. So let me draw the pressure volume diagram for this toy model cycle. So this would be the point for the low pressure, low volume, high pressure and low volume, high pressure and high volume, and high volume, low pressure. Let me give labels for these different pressure and volume points. Alright, so this is a pretty simple cycle that makes calculations easy. All these processes are isochoric, isobaric, isochoric, isobaric processes that makes calculation of work done fairly simple, and we'll be able to do this question using only algebra, no calculus needed. And having drawn this diagram, I can tell you that this completely specifies our system. This is through the ideal gas law. Pressure times volume is equal to nKT. Okay, maybe not completely specified. The number of gas molecules is still left as unknown. So if the question were to give you how many number of molecules there are, then it is completely specified. For every point along the cycle, you can actually calculate the temperature. All right, so here are the questions that we would ask in analyzing any heat engine cycle. They are, what is the net work done? It's kind of important. It points at the entire purpose of a heat engine. And for Regens's-Wheel oscillator, it's important to know how much heat was transferred into the system. We'll call it QH for heat transfer at high temperature. And also for Regens's-Wheel oscillator, the heat output from the system is also important, which we'll label QL, heat exchange at low temperature. Now here, work done calculation is actually easy. Let's say we are starting at point A. Then the system undergoes isochoric heating, reaching point B. No work is done throughout this process because the volume doesn't change. And then the system undergoes isobaric expansion, reaching point C. It does some work. That would be the area under the curve here. Then as the system undergoes isochoric cooling, reaching point D, no work is done again, no change in volume. And then as the system goes back to point A, undergoing isobaric contraction, the system does negative work, or rather the environment does work on the system. So the negative work with magnitude equal to the area under the curve is done. So when you calculate the net work done over a cycle, it's the area enclosed by the loop, or this area in green here. Alright, so it seems like network calculation won't be that difficult. Some of you probably have an answer right now already. So what the point of the next 15 minutes or so is going to be is actually calculating the net heat flow. So on this PV diagram, the information about heat isn't readily apparent here. So it must be calculated. This is where we are going to use the first law of thermodynamics. Change in internal energy is equal to net heat flow minus the work done by the system. All right, let's dig in. Let's just start from point A to B. So we can start by figuring out the amount of work done. That was easy. Now, as I said earlier, knowing pressure and volume specify the temperature. So we can calculate the change in internal energy. Oh, but we are going to specify a little bit more. So I guess for this system, I'll have to say it's a monatomic gas. And I hope you remember from earlier chapter that for monatomic gas, internal energy is given by 3/2 nkt. So they don't actually need to specify the number of molecules. I can re-express this in terms of pressure and volume. This is just the 3/2 pressure times volume, right? So for the process A to B, change in internal energy is 3/2 PHVL, final point, minus the initial point, PLVL. Alright, since the work done was 0, this is equal to heat transfer along the process A to B. Now, if you look at this expression, you can see that that's going to be a positive number. So there's a heat input into the system as the system goes from A to B. Alright, let's keep talking through. So process B to C. Here the work done isn't 0. It's pressure times change in volume. You can see that it's doing positive work. And the change in internal energy is 3/2 times difference in pressure times volume. I'm going to keep them as separate terms because that's going to make our later algebra a little bit easier. Now this time, this isn't the heat transferred. We have to use the first law. That is, heat transferred is change in internal energy plus the work done by the system. Alright, that looks a little bit complicated. Let me do the algebra on a separate piece of paper and then just write down the result here. Alright, there it is. So if you look at the expression carefully, you can say it's a positive. So there's a heat input going from B to C here also. Now, I can sense that for the next two processes, CD and DA, there will be heat outflow. So this seems like a good location to pause for a bit and calculate the heat input, QH here. So QH is QAB plus QBC. Let me again write that down on a separate piece of paper and copy the result here. I have canceled out some terms, and this is the result. Let me highlight it so that I can find it on this very complicated page easily. Alright, let's keep going. Process C to D. Again, work done is 0. It's an isochoric process, no change in volume. For the change of internal energy, it's the same deal. 3/2 times the difference in pressure times volume. And since work done is 0, this is going to be equal to the heat exchange from C to D. Now, I don't want you to miss it. I want you to see that when you stare at this expression, this is going to be negative. So heat flows out of the system in the process C to D. Alright, let's keep going. D to A, back to the starting point. So here there's a non-zero work done, pressure times the difference in volume, and because the ending volume is smaller than the starting volume, the work done is negative, meaning the environment does work on the system. Change in the internal energy is the same as before, 3/2 times change in pressure times volume. And as before, because there's work done, the net transfer is not just the change in internal energy, but the change in internal energy plus work done. Or, writing it aloud, 5/2 PLVL minus, again 5/2 PLVH. So that's the result. And when you look at this expression carefully, you can see that it's a negative quantity. That means as the gas undergoes process D to A, there's a heat outflow. Alright, that completes the cycle, and we should calculate QL, the net heat outflow from the system over a cycle. Now, by convention, both the QH and QL are defined to be positive quantities. All the formulas used in your textbook will assume that. So here, instead of adding QCD and QDA, I will calculate the minus of QCD plus QDA. This will give us the positive quantity we are looking for. Alright, this is going to take a little bit of algebra, so I'll do it on a separate piece of paper and write it down here. Writing down the positive quantities first. Alright, let me highlight this quantity so that I can find this expression easily in a little bit when I'm looking for it. Alright, that's it. That was a little bit of tedious calculation, but we are almost done. We need to calculate the network, which would be work done along BC plus the work done along DA. This is negative. So let me do that and write it down, factoring it as needed. Alright, we are done. This is probably what many of you guessed a while back when we talked about the area enclosed by the curve being the network done. So with these results, there are a couple interesting things you can do. I guess I will leave you to do one of them and I will work out the other thing in this video. So one of them you can do is, this is what we would claim based on conservation of energy, that the net work done must be equal to heat transfer into the system minus the heat transfer out of the system over one cycle. You can show that from the algebraic expressions we have derived. I'll leave that for you. What I want to do is a bit more interesting. I want to help you start developing some number sense for these thermodynamic problems, which is also going to be important when we start talking about efficiency and second law of thermodynamics. So let me just assign some reasonable numbers for this pressure and volume. So let's say that the high pressure is about 2 atmosphere, or approximately 200 kilopascals, or 2 times 10 to the 5 pascals. And let's say that the low pressure is half that, about 1 atmosphere, or 10 to the 5 pascals. Let's have some reasonable volume numbers too. Let's say that the high volume is 2 liters, or 2,000 of a cubic meter. Everyone here can imagine what 2 liters looks like, right? Imagine a large soda bottle. And the low volume is, let's say, half that. Alright, so what we are going to do is we are going to calculate some numbers based on these given parameters. Now watch how I don't have to specify the number of gas molecules. If I have few molecules, it means the thing is at high temperature. If I have large number of molecules, it means the thing is at low temperature. Alright, let me make some space here, taking care not to erase the expressions I need. Alright, I think I avoided erasing anything important. So as a reminder, this is QH and this is QL. Alright, so the work done is pretty easy to calculate, so let's do that. That's the difference in the pressures, that's 10 to 5 Pascal, times the difference in the volume, that's 10 to minus 3 cubic meter. And since these are basic SI units, I'm just going to trust that the units work out to unit of joule, which is what it's supposed to be. So 10 to 2, that would be 100 joules. Alright, that's a fairly reasonable number. Oh, let me move these two things so that there's some space to write down the numbers. Alright, and let's plug in the numbers for QH and QL. The heat input is, let me pre-simplify some numbers. And all of this is going to be in joules. So power of 10 is 10 to the 2, so we're going to multiply by 100 later. 4 times 5 over 2, so 10 minus 2 minus 1.5 is 6.5 times 100 joules, or 650 joules. Does this number seem large to you compared to the work done? Yeah, it's pretty large, and that's what I mean by number sense. So actually, without doing any further calculation, because you can read this here, the net work done is QH minus QL, you can kind of figure out what QL is. And if you doubt me, you can plug in the numbers and do it for yourself. So here QL is going to be 550 joules. I just want you to look at these numbers here. In this heat engine, when 650 joule of heat energy comes in, of that, only 100 joule is turned into mechanical work. And a vast majority of the input energy is expelled as what we are later going to call waste heat. So I think that's everything we can do with this toy model here. I'll have one more toy model for you to look at where the calculation is still relatively simple, and we can again plug in the numbers and get some intuitive feel for it. Hi, this is a continuation of heat engine cycle examples, part 1. We'll look at toy model number 2. So this is still a toy model. It's not a representation of a realistic heat engine cycle, but it's an illustrative example that'll show you some calculational techniques and what you will need to know when you are ready to analyze a realistic heat engine cycle in part 2 of these videos. So let me sketch out the thermodynamic process here. We start from the low pressure, low volume, and the system undergoes isochoric heating, reaching the high pressure point, and then it's going to undergo isothermal expansion. This curve is supposed to look like 1 over x or 1 over v. And the system undergoes isobaric contraction. Alright, we are asking the same questions as before. That is, what are the net work done and the heat transfers. And we went through this before, so let me write down the equations that you are going to need. The ideal gas law, the first law of thermodynamics, and the expression for the internal energy. Let's say it's a monatomic gas. This can also be expressed in terms of purely pressure and volume with the help of the ideal gas law. Alright, so we'll refer to these as needed. So without further ado, let's start the analysis. So let's say this system starts from this point, A, undergoes isochoric heating, reaching point B, undergoes isothermal expansion, reaching point C, and then returns to the original point by isobaric contraction. Alright, so the process from A to B looks very much similar to what we analyzed before. In fact, it's the same process. So let's go through it. The net work done is 0, no change in volume, and change in internal energy is 3/2 times the difference of pressure times volume. So the ending pressure times volume, high pressure times low volume, minus 3/2 low pressure times low volume. And since the work done is 0, this amount of internal energy change is due to the heat transferred from A to B. If you look at this expression carefully, you can see that it's positive. So that means there's a heat inflow during this isochoric heating. Kinda makes sense. Now, the thermodynamic process from B to C is interesting. So here, instead of being able to say something about work right away, we can actually say something about the internal energy change right away. If it's isothermal, that means temperature isn't changing, so internal energy is not changing. So that means from the first law of thermodynamics, we can say the heat transfer from B to C is equal to the work done. Now, it's not that easy. There's a bit of a problem we have to work out here, in that the pressure changes throughout this process. So we can't just say work done is pressure times change in volume. Instead, we need to say that the infinitesimal amount of work done is equal to pressure times the infinitesimal change in volume. And in order to calculate the total amount of work done, we would need to integrate from point B to C. Alright, so this is where we use the ideal gas law to express the pressure here in terms of volume, the integration variable, and other things that are hopefully constant. Now, because it's an isothermal process, the temperature here is constant. In fact, let me put a little subscript, T sub H, so that I know that it's a number. It's not temperature as a variable, it's a temperature along that isotherm that the process is taking place. The volume is changing from the low volume to the high volume. Alright, I think I know how to do this integral. Integral of 1 over x is natural log of x. So factor out the constants, nkt, times the antiderivative, evaluated from the low limit to the high limit. Now, when you plug in those limits, this is what you get. Natural log of VH minus natural log of VL. And doing a little bit of logarithm algebra, we get natural log of VH over VL. As you will see later, that form is going to be more useful, so let me write that in instead. And as I wrote earlier, this is the heat transfer from B to C. Carefully looking at this number here, since VH is greater than VL, this is a positive number. That means there's a heat inflow during this expansion here. Alright, I think that's all of the heat input. So this is a good point to pause for a bit and calculate the heat input to the system. So heat input is equal to heat input in process A to B plus heat input process B to C. And it doesn't really simplify here, so I'll just write it down. I can do one simplification. Instead of writing this in terms of temperature, I can write it in terms of pressure and volume. This would be equal to high pressure times the low volume. So with that, this is the expression for the total heat input. Alright, let me highlight this so that I can find this easily later. Okay, we have one more process left. The isobaric contraction from C back to A. I think we've done this before. So there is work done. That's the end point, PLVL, minus the starting point, PLVH. And looking at this carefully, you can see that this is negative. Alright. Change in internal energy is calculated the same way as the previous example. It's 3/2 the ending point, PLVL, minus 3/2 the starting point, PLVH. So the heat transferred is calculated using first law of thermodynamics. Change in internal energy plus the work done is equal to 5/2 PLVL minus 5/2 PLVH. Staring at this for a bit, you can see that this is negative. So that means the heat flows out of the system in this isobaric compression. In fact, that's the only segment where heat flows out of the system. So this gives the QL. Or rather, QL is the minus of this, since it's by convention defined to be positive. Alright, let me highlight this so that I can find it later. Alright, so those are the heat transfers. Let me write out the net work done, which is the work done in the step B to C plus the work done in the step C to A. It's already negative. So combining those two results, we get Alright, it doesn't really simplify. I guess we better plug in numbers to see what that looks like. Alright, so as before, you can algebraically verify that the net work done is equal to QH minus QL. But let me leave that to you. You can do that on your own if you want to. As before, I want to plug in some interesting numbers to continue to develop our number sense. Let's pick numbers that are comparable to what we picked for toy model number 1. So let's say that the low pressure is approximately 1 atmosphere or 10 to the 5 pascals. Now, in toy model number 1, we chose the high pressure to be double this, but I want to make the temperatures comparable for the reasons you'll see later. So that means the highest temperature point in toy model 1 was the 4 times the lowest temperature, since it's double the pressure, double the volume. So I'm going to make this high pressure point be equal to 4 times 10 to 5 Pascal. So the low volume point should be similar, so 1 liter or 10 to minus 3 cubic meter. And as it turns out, because we specified this process to be isothermal, we don't actually have freedom to pick our high volume point. This has to be pH over PL times VL. So our high volume point has to be 4 liters. Alright, let me clear out some space here so that I can plug in numbers. Alright, so the net work done is pH times VL, that's 400 joules, times the natural log of 4, plus PLVL, or 100 joules, minus PLVH, or 400 joules. So I'm going to have to use calculator for this. Alright, my calculator says that the work done is about 255 joules. Huh, that's interesting. Alright, let's calculate the heat expelled from the system. Let me move this so that there's room to write numbers. So plugging the numbers, 5 halves PLVH, or 400 joules, minus 5 halves PLVL, or 100 joules. That's equal to 300 divided by 2, 150 times 5, 750. Now, like before, we can use conservation of energy to figure that QH must be work done plus QL, or 1005. So when you look at these numbers, it looks a little bit better here. This is about 25% of the input heat, whereas before 100 out of 650 was close to 15%. So proportionally, greater portion of the input heat is being turned into work. Now, you might wonder what's allowing this toy model number 2 to be more efficient compared to the toy model number 1. And when we come back for heat engine cycle examples part 2, we are going to look at a theoretical heat engine cycle that was devised to maximize the percentage of input energy that's turned into mechanical work. It's called the Carnot cycle, and we'll come to that when we get there. But the calculation there is a little more involved, so we'll reserve that until later. So until then, bye. Hi, this is a heat engine cycle example video on Carnot cycles. Let me start out with a PV diagram. Because the Carnot cycle is a purely theoretical cycle, it's difficult to start out with a physically intuitive place. So let me just start out at the high pressure, low volume point. You might call this the point where the engine has the most energy and it's about to do work. It's not technically true, but let's start there. So from this point, the engine undergoes an isothermal expansion from A to B. And this follows an isotherm, a curve on a PV diagram that indicates constant temperature. Let me call this TH for high temperature. Then at point B, the gas undergoes further expansion, this time adiabatically. Zero heat transfer, so the temperature of the gas goes down. This slope is steeper, so the state of the gas ends up on a different isotherm. This isotherm might be associated with temperature TL, low temperature. After this, the gas undergoes isothermal compression, reaching point D. And D is exactly the right point where if the gas undergoes further adiabatic compression, then it'll reach point A, completing the cycle. So that's the Carnot cycle. For the process from A to B, isothermal expansion, there's going to be a heat inflow so that the gas can remain at constant temperature while it's doing work. And since there is no heat exchange along the process BC, this is actually going to be our heat input, QH. And along the isothermal compression, C to D, there's going to be heat outflow from the gas, so that once again the temperature will remain constant while work is being done on the gas. And since the heat exchange from D to A is 0 again, we can call this QL, our heat outflow. Alright, so we ask the same questions as before. That is, what are the net work done, heat input, and the heat output? Let me write down some equations that will be useful as we work through this example. There's the ideal gas law, as usual, and the first law of thermodynamics. And assuming this is a monatomic gas, we have following expressions. One of them you have seen, the internal energy of the gas. And the other is the adiabatic relationship. This was derived in, I think, chapter 3. What was derived was there was a relationship between pressure and volume in an adiabatic process. And the relationship is that pressure times volume raised to some numerical factor gamma is constant. And what this gamma is depends on the type of gas. It's defined as the specific capacity under constant pressure over specific capacity under constant volume. And for monatomic gas, this turns out to be 5/3. And if you go back in the chapter and read it, this is related to the degree of freedom that's expressed in the internal energy. It's all very interesting, but for us, it'll actually turn out that gamma cancels out anyway, but in some questions this might be relevant, especially numerical questions that give you some specific quantities and ask you for some specific quantities. Alright, I think that's all the preliminary information and we are ready to jump right in. So let's just start with the process A to B, the isothermal process. We've done this before in a TOEIC example, TOEIC model 2. So because it's isothermal, we can start out with a statement about the internal energy change. We can say it didn't change. So that means from the first law of thermodynamics, that heat exchange from A to B is equal to the work done along that path. And we worked this all out before, so because pressure is changing, we have to express this as the integral of the infinitesimal amount of work done, or pressure times the infinitesimal volume integrated from point A to B. We can re-express pressure in terms of volume using the ideal gas law, nKT over V. Here the temperature is constant, so let me put a subscript to remind me it's actually just a number. And the integral goes from volume A to volume B. So here, as you can see, there are many different pressures and volumes. So I'm just going to specify any particular value using the subscripts. It'll turn out that because of these constraining relationships between pressure and volume, that there's really only about 2 free parameters here. But until we reduce it down, I'll just use a subscript. Alright, so we've done this integral before, so let me just write down the result without wasting too much time. The antiderivative of 1/v is natural log of v, plug in the limit, I get nkt times the natural log of VB over VA. And this result is greater than 0, as we should expect. The gas is doing positive work, so there must be heat inflow into the system to allow it to do this work without change in internal energy. Alright, so this time I'm going to leave my answer in terms of the temperature because I have a sixth sense about that being path to simpler expressions. Alright, let's look at process B to C. This is new. It's an adiabatic process, and that means by definition, heat transferred during this process is 0. Alright, so that's interesting. Let's look at the first law of thermodynamics. So Q being 0 means that the work done is minus of the change in internal energy. And because we are given the temperatures, or at least I'm pretending they're given, it'll turn out that that's actually a quicker way to calculate work than to try to calculate work by using definition of work. So we're going to do that. So the change in internal energy is 3/2 nk final temperature minus the initial temperature. Or working out all these double negatives, we get 3/2 nk th minus tl. Alright, that was surprisingly simple. If we had gone the longer route involving the definition of work, well, it would have taken longer. We would have to do the integral, and I don't have space for that here. Alright, let's keep going. The process from C to D is very similar to A to B. It's an isothermal process, so change in internal energy is still 0, which means the heat flow in the process C to D is equal to the work done again. So you can set up all the same things we did before. Let me just write down the result here. It's going to be nk times the temperature, different constant that's involved here, TL, times the natural log of the ratio of the final volume over the initial volume. Now, I see that VD over VC is less than 1, so this natural log is going to be negative. So let me use a little bit of logarithm algebra to make that negativeness more obvious here. I was treating that VD over VC as VC over VD raised to power of minus 1, and then pull out the minus 1, and that's where the minus 1 comes from. Now it's clear that this quantity is less than 0, so work is being done on the gas. So the heat must flow out of the system so that the internal energy doesn't increase. Alright, the final step here, D to A. So in D to A, the compression continues, but because the heat exchange is now 0, internal energy is allowed to rise, and we can use that change in internal energy to calculate the work done. The exact same thing we did for B to C, except this time we expect the change in internal energy to be positive, increasing, so the work done will be negative to indicate work being done on the system rather than by the system. So since it's the exact same calculation, let me just write down the results. You've seen the process before. Since TL is smaller than TH, I know this is negative, so let me pull out the negative to make its negativeness clearer. Less than 0, work is being done on the gas. Alright, let's start out with the first question. What is the net work done? And as you look at the expressions we derived, I hope you notice something interesting. The work done during adiabatic expansion B to C is equally magnitude to the work done on the gas during the adiabatic compression from D to A, and opposite in sign. So these work done during adiabatic expansion and compression will just cancel each other out, and we only need to calculate the net work between the isothermal expansion and isothermal contraction. Alright, let me write that out. nk/th times the natural log of VB over VA, and I'm adding the other thing, so minus nkBTL times natural log of VC over VD. This is probably a good point at which to reduce the number of variables we have in our expression. VB, VA, VC, and VD. I think I'll be able to express the ratio VC over VD in terms of the ratio VB over VA. Let me make a little space here to work that out. Alright, so that's probably enough space. So the point C is related to point B by adiabatic process. So that means this relationship holds. PB VB raised to gamma is equal to PC VC raised to gamma. Alright, and I also need one for VD, which is connected to A by adiabatic process. So PA VA raised to gamma is equal to PD VD raised to gamma. Oh, so I can just take the ratio of these two equations and I'll get something that simplifies to a degree. PB over PA times parenthesis VB over VA raised to gamma is equal to PC over PD times parenthesis again VC over VD raised to gamma. Now here's the fact I'm going to use. The points B and A are related by isothermal process, which means this ratio can actually be related to the ratio volumes. In fact, this is PB over PA is equal to VA over VB, or you could say this is VB over VA raised to power of -1. So I can actually combine this ratio with the existing ratios just by changing gamma to gamma -1. And I can do the same thing here because the points C and D are related by isothermal process. So this amounts to being the ratio VD over VC. So I can just modify this as gamma -1 here. So this is the relationship you end up with. VB over VA raised to the factor gamma -1 is equal to VC over VD raised to factor gamma -1. And since it's the same power, that actually means VC over VD is equal to VB over VA. So I can do this. Get rid of this raising to the power of gamma -1 and say VC over VD is equal to VB over VA. Alright, let me make the change here and change VC over VD with the VB over VA. Then we can simplify this more by factoring out all the common factors, NK, natural log of ratio volumes, times the temperature difference, TH minus TL. It's a surprisingly simple expression for the network done. This is what I mean. Carnot cycle is a simple process. It's designed to make the thermodynamic properties very simple. The heat input is here. It's this one heat input that we already calculated. This is our QH. And QL comes directly from the quantity we calculated for the process C2D. Let me just make the quantity positive and make the substitution we just discovered. That's it. We are done. Now, there are some additional questions we can ask here, but let me do that in the summary video, comparing all 4 realistic heat engine cycles that we will compare to each other. For now, this is complete set of expressions to work with, and I'll save these highlighted quantities for later reference in the summary video. Until then, bye. Hi, this is a video on examples of heat engine cycles. And in this video, we'll look at the Otto cycle. Otto cycle is an idealized version of the processes that occur in common automobile engines. Let me show that to you on the Wikipedia page. This is the Wikipedia page for the Otto cycle. For us, what matters is really down here. The Otto cycle is constructed from, and this is the pressure volume diagram for the cycle. For us, this blue and green horizontal lines don't really matter. It is important for the real functioning of the engine. That's where the fuel exhaust is expelled and new air is taken in. But for our purposes, what we care about is the cycle, starting from 1, 2, 3, 4, and back to 1. So from 1 to 2, that's adiabatic compression. So this is where the piston compresses the fuel-air mixture. We assume it happens quickly enough that no heat is exchanged with the surrounding. And at point 2, this is the very important point. This is where the fuel-air exhaust is ignited with an electric spark. So this happens quickly enough that the volume doesn't have any time to change. So this is idealized with isochoric heating. And the temperature that it reaches at point 3 is determined by something called adiabatic flame temperature of the fuel-air mixture. You can look it up later, or I will look it up when I do the summary video to compare all these different cycles with each other. Now, from this point 3, high pressure, low volume point, the gas expands adiabatically doing work. And this is what we sometimes call power stroke. This is the part of the engine cycle that actually does work. And once it reaches point 4, then it needs to return to the original point somehow. In a real engine, it expels the exhaust, takes in the fresh air at room temperature. We're just going to say that there's an idealized isochoric process that somehow takes the engine from 4 to 1. That completes the cycle and it's ready to do the work again. So for our analysis, what's important are these processes connecting each of the steps. Adiabatic compression, isochoric heating, adiabatic expansion, and isochoric cooling. And we'll ignore all the other technical details for the time being. Alright, back to our notebook. I copied the PV diagram from the Wikipedia page so that I don't have to redraw it. So we are asking the same questions as before. That is, what are the net work done and the heat transfers. The result for the Otto cycle will be a little bit more complicated, so I'll try to go through this quickly. Let me start by relabeling some of these points. I'm going to call this A, my starting point, B, C, D. And let me label some parameters we'll be using. So the low volume, VL, that's the volume at A and B, and the high volume, VH, that's the volume at C and D. And we can see that point B is at the highest temperature, so we are going to call that TH, high temperature. It'll be important for the comparison purposes later. And we can see that D is at the lowest temperature, so we'll call the temperature at D TL, the low temperature. The temperatures at C and A are going to be something in between, so we'll have to introduce a parameter for that later, and then from the information here kind of eliminate it. Alright, as before, let me write down all the equations that we are going to be using. The ideal gas law, the first law of thermodynamics, and for monatomic ideal gas, the internal energy, and the adiabatic relationship. Alright, I want to go through this kind of quickly because we've went through all these processes before. What will take more work isn't working out the work and heat exchanges initially, but it'll be the algebra we need to do to try to reduce the number of unknowns. So let me write down all the basic expressions for each of steps first. So from A to B, this is isochoric heating. We've done this before. No work is done. And the heat input is equal to change of the internal energy. I can write this in terms of the difference in temperature, but using ideal gas law, I'm going to rewrite it in terms of pressure and volume. And later on, we'll eliminate these additional unknowns we just introduced. And one more thing, I'm labeling this as QH because that's the only place where there's a heat input to the system. Alright, process B to C, that's adiabatic expansion. So adiabatic means no heat transfer. And the work done is minus of the change of internal energy. Let me express this one in terms of temperatures. Making sure I'm not making any sign errors. This is positive as it's supposed to be. And this TC is an additional unknown I'm introducing that we're going to have to eliminate later. Isochoric cooling from C to D. Once again, no work is done. And this is the heat exhaust, which is given by the change of internal energy. And I'm going to express that in terms of pressure and volume again. And PD and PCR, new unknowns I'm introducing that we'll eliminate later. And making sure there are no sign errors. This is negative as it's supposed to be for heat outflow from the system. Alright, final step, D2A, adiabatic compression. So heat exchange is 0 again. And for the work done, we look to the change of internal energy again. TA is another unknown I have to introduce. That's temperature at point A. And since it's supposed to be greater than the lowest temperature, this is negative quantity as it's supposed to be. Alright, so that's ostensibly everything we need. The heat transfers and the work done. But we've introduced 1, 2, 3, 4, 5, 6 unknowns that we're going to have to try to get rid of. Some of these are a little bit easier to get rid of. Let me write those down first. Pressures at point B and D are easy to get rid of because I know the temperature and volume at those points. So the remainder are a little bit harder, but tackling TC and TA will be easier. So let me do that first. The approach here is to utilize the adiabatic relationship that we know. C is related to B by adiabatic process, so we can say this. Let me rewrite this in a slightly more suggestive form. I did that because when you have pressure times volume, you can relate that to the temperature directly using the ideal gas law. So we get this. At point B, the temperature is TH and the volume is VL. And I can express the temperature at point C. And at point C, volume is VH. Some things nicely cancel out. And we can solve this for TC here. And we can imagine going through similar calculation with the TA. I'll leave it to you to do the step-by-step calculation. Let me write down the result here. Alright, if necessary, pause and make sure that these results make sense. I'm going to erase the derivations and save these two expressions here so that we can use them in reducing the number of unknowns. Alright, if you missed the derivations, you can always go back in the video and look at it again. Alright, that takes care of the unknown temperatures. And now we have the tools to handle pressure at point A and pressure at point C. Because now we know the temperature at those points. Or if you plug in the expression for TA from our derived result, I combine the factors of VL together. And we can do the same thing for pressure at point C. Alright, so this is one of those problems where there isn't much to be gained by doing extensive algebra because these expressions don't really simplify when you combine them algebraically. So I'm just going to write out the network and the heat transfers in terms of these expressions. And when we get to the summary video, I will use these expressions to work out the numerical values of these parameters and plug them into the formulas I'm going to write down right now. The net work done is 3/2 NK times TH plus TL minus TA minus TC. And the heat inflow QH is 3/2 PB minus PA VL. And the heat outflow is 3/2 PD minus PC. Alright, so we'll come back to this later when we are doing the summary video. Alright, so before I go, I just want to point out one thing. This quantity here, it's not guaranteed to be positive. It comes down to a matter of picking correct parameters, because both the isochoric processes and the adiabatic processes change temperatures. So you need to make sure when you pick the parameters for this, that in the adiabatic expansion, the temperature doesn't decrease so much that you go below the TL. That would make the whole thing nonsensical. So I'll take care of that when I do the summary video. Hi, we are continuing with the heat engine cycle examples, and this is on diesel cycle. The diesel cycle is idealized version of a heat engine cycle, describing the second of the common internal combustion engines. Let me show you the Wikipedia page. So this is the Wikipedia page for the diesel cycle. And one interesting thing about diesel engine is that the fuel is ignited by the temperature rise due to the adiabatic compression. You have seen that demo of the fire syringe, and it's not just a lecture demo. It is an integral part of an actual working heat engine. For our present purpose, what's more important is the cycle itself. So this is the idealized diesel cycle. You can see that it's very similar to the Otto cycle. Both the expansion and the compression is adiabatic. We will contrast this with the Stirling engine, which is the only non-internal combustion engine that we'll talk about as far as the real engines go. So those features are similar, and they are also similar in that there's this idealized isochoric cooling process, which is idealizing what is a very complicated real-world process. And the one key difference here is for the Otto cycle, the switch between two adiabatic curves happened by isochoric heating. In the Otto cycle, the assumption was that volume is mostly the same, it's the pressure that changes. With the diesel cycle, the idealization happens the other way. The pressure is constant and it's the volume that changes. And you can read about it on the Wikipedia page. Apparently in a real diesel engine, the pressure does change, but for us, this is the cycle we'll analyze. Alright, back to our notebook. So I copied over the PV diagram here from the Wikipedia page so that I don't have to redraw everything. But it looks like this diagram is a little bit overdefined. So let me label the parameters that we will actually use. So let me first relabel the points in the order I plan to go in. Let me label this A. We're gonna start here, B, C, and D. So for comparison with the other cycles that we'll look at, we are going to need to specify the highest temperature, which is going to be at point B. And we are going to need to specify the lowest temperature, which is going to be at point D. And let me cross out the parameters that we are not going to use to specify our system, because as I was saying, right now this system is overdefined. All the parameters you see labeled are not actually free parameters. So I think I'm not going to use this volume to specify the system. I don't think I need any of these two pressures to specify the system. And I don't think I need this pressure here to specify the system. Although it is a good way to label it since I have a constant pressure thing here. But especially for the comparison with the Otto cycle, I think the better parameters to retain are these. The volume here, which I'm going to relabel as V sub H for high volume, and the volume here, which I'm going to relabel as V sub L for low volume. Alright, these four parameters should completely specify this system. So let's get started. So we are asking the same question as always. What are the net work done and the heat transfers? And let me write down all the equations we have been using. Those haven't really changed. the ideal gas law, first law of thermodynamics, and for monatomic gases, the expression for the internal energy, and the adiabatic relationship. Alright, let's get started. Like with Otto cycle, I want to get through this quickly. I'm really only doing this for comparison. Okay, so for A to B, the isobaric expansion, we haven't had this in a while, but hopefully you remember how this goes. With the isobaric expansion, the work done can be expressed simply algebraically. So the work done is pressure at point A times the change in volume. Volume at B minus volume at A, which is V sub L, the low volume. And as before with the Otto cycle, I'm using the subscripts to indicate the quantities associated with a point, with the goal of replacing those eventually in terms of known quantities. I hope you remember isobaric expansion being complicated. There's non-zero work done, and there's non-zero change in internal energy, because there's a change in temperature. This is the familiar expression from the previous examples. And temperature at A is known, we'll figure that out later. And finally, we use first law to express the heat input, which is going to be change in internal energy plus the work done by gas. So let me just write that out. Alright, let's keep going. The adiabatic expansion from B to C. So now things get easier. The heat transfer is zero, it's adiabatic. So we can say that the work done is minus of change of internal energy. And we can express that in terms of the temperatures. The temperature at point C is lower than the hottest temperature, so this is positive, as we expect it to be. Because there are so many minus signs, I want to make sure I didn't make a sign error. Alright, chugging along. Isochoric cooling from C to D. So here the work done is zero, and all the heat transferred goes into changing the internal energy. Make sure this is negative because there's heat flowing out from the system for this step. Alright, finally, the adiabatic compression from D to A that completes the cycle. Since it's adiabatic, heat transfer is zero, and the work done is minus of the change of internal energy. And double check that this quantity is negative, as it's supposed to be for work done on the gas, and temperature at point A is larger than the lowest temperature. Alright, so these are all our expressions, and so we wrote this all down, introducing as many unknowns as we want to use. Now we should track them and make sure we have a way of finding them out. So let me highlight the unknowns in cyan. I don't know the pressure at A, I don't know the volume at B, and I don't know the temperature at A. And I'm not going to highlight a quantity that I already highlighted before because that'll mess up with my unknown count. And the last that I haven't highlighted is temperature at C. Alright, not as many unknowns as I feared, only 4. So figuring out these unknowns is where all the expressions we wrote down comes in. And looking at it, I think the easiest thing to figure out is temperature at A. It's connected adiabatically to point D, and I know everything I need to know at points D and A to express the temperature at A. So I went through this derivation when I did the Otto cycle, so I won't go through it again. But as a reminder, this is the result in Otto cycle. So in Otto cycle, we had this result. Temperature at A is TL times the ratio of the two volumes, high over low, raised to the power of gamma minus 1. And this is actually going to be valid for my diesel cycle too. So let me write that down on the other page. The temperature at point A is equal to the low temperature times the ratio of the volumes raised to the power of gamma minus 1. Alright, Now treating this temperature at A as a known quantity, I'm going to express one of the other unknowns. This is all going to be chained together. So the next quantity I can figure out easily is pressure at A, because now I know the volume and temperature. I can use the ideal gas law to say pressure at A is equal to NkTA, which now I know, over VL. Alright, so now I'm going to treat this as another known quantity. If I know pressure at A, then I know pressure at B, where I know the temperature. That means I can express the volume there. So the volume at B is, using the ideal gas law again, NkTH divided by the pressure at A, which is also pressure at B. Alright, so that's another known quantity. Now that I know the volume at B, I can express temperature at C through the same formula as this one here. I'm just gonna try to remember it from my memory. It is Tc is equal to, I relate it to the temperature at point B, which is the high temperature, times, and it's lower, so it must be volume at B divided by volume high, raised to the power of gamma minus 1. Alright, so that's the temperature at C. So like with Otto cycle, I'm not going to work this out algebraically because there's no real payoff to look forward to. But these are enough formulas that I can do the comparison numerically when I get to the summary video. Let me highlight a few more quantities. This is the heat input. Got that on the first try. Now the heat output, I need to express it as positive quantity. So it does come from here, but I need to express it as a positive quantity. QL is equal to 3/2 NK TC minus TL. And finally, I can write down the work done. And the work done is the sum of the three contributions from A to B, B to C, and D to A. Alright, that's enough. These are all in terms of quantities I know, so I can now plug in the numbers if I'm given the low volume, high volume, and the temperatures. So we'll be using these results for the summary video. Hi, we are continuing with heat engine cycle examples, and in this video we'll cover Stirling cycle. Stirling cycle is an interesting example. It's the idealized cycle for the Stirling engine, which isn't as common as the Otto engine or diesel engine, but it is the only example of I guess you could call it external combustion engine. Let me show you the Wikipedia page for the Stirling cycle. So this is the Wikipedia page for the Stirling cycle, and there's an interesting history behind the Stirling engine. You can read about it on your own. Let me scroll down here for the cycle. So this is the idealized Stirling cycle, and you can kind of see what I mean. It is not an internal combustion engine on the cycle itself. Here the curves, they are not adiabatic, they are isothermal. So the idealization with the Stirling engine is that as the gas expands, it's in thermal equilibrium with the thermal reservoir. The heat isn't coming from a single combustion within the engine, it's coming from an external source that's continuously transferring heat. So this is the kind of idealized model, but we have an actual working lecture demo model, the video of which you can see elsewhere. Alright, so for the purpose of current analysis, we are analyzing this. So we'll start from here: isochoric heating, isothermal expansion, isochoric cooling, and then isothermal contraction. Alright, I copied the PV diagram over so I don't have to read over everything. Let me label the points I'll refer to. Point A, we'll start from here. B, C, and D. And let me label some parameters that we'll use to define and compare this cycle with the other cycles we've been covering. So we need a temperature for this upper isotherm. I could call this TH. That matches what we've been using. And we need a temperature for this lower isotherm, and I can call that TL for lower temperature. Alright, I think I only need two more parameters, the high volume and the low volume. Alright, I guess that's everything. So we are asking the same question as before, that is, what are the net work done and the heat transfers. And as before, let me write down all the formulas we'll need. There's the ideal gas law, the first law of thermodynamics, and for monatomic gases, the expression for the internal energy, and the adiabatic relationship. Alright, that's it. We've done this enough. Alright, so let's get started. The first process is isochoric heating from A to B. Since it's isochoric, the work done is 0. Nice and easy. So the first law says that the heat transferred from A to B is equal to the change of internal energy. We've done this many times before, so I first wrote it using the expression for the internal energy and then rewrote it in terms of pressure and volume since it's more useful. Alright, now the isothermal expansion, B to C. Since it's isothermal, it says that the change of internal energy is 0. And the heat transferred is equal to the work done, which we have to calculate by integrating pressure times volume from B to C. We've done this many times, so let me write down the result here. If you want to find the process, you can go look at the video for the Carnot cycle or the video for the toy model 2. Alright, make sure that result looks correct. One check we can do for both of them is that they are positive, and it should be in both steps. In both cases, the heat is flowing into the system, either to fuel the rise in the internal energy or to fuel the work done without any decrease in the internal energy. Alright, let's keep going. Isochoric cooling from C to D. This is the reverse of A to B, so the work done is still 0, and the heat transferred is the change of internal energy, which is going to turn out to be negative this time. PD is smaller than PC, so this is negative. Alright, the final step, the isothermal contraction, D to A, completing the cycle. As before, change in the internal energy is 0. That's what isothermal means. So the heat transfer has to be equal to the work done. And I'm just going to write down the result here. Hopefully you can double check that it's correct. And check that it's negative, as it's supposed to be. Alright, that's it. Let's write down the network and the heat transfers and see what we can get from that. So work is only done along the curves BC and DA. So adding those two together, I'm going to use the logarithm algebra to turn this into the same thing as this. You get the following result for network. If you remember the result from Carnot cycle, this is the same result as the Carnot cycle result. If you are surprised, I hope you are not surprised, because in the Carnot cycle, the work done along the adiabatic paths canceled out. So whether it's adiabatic or isochoric, it kind of doesn't make a difference since they cancel out to 0 either case. Now, this is not the Carnot cycle, and the difference mainly comes in the amount of heat transferred. For the Carnot cycle, for the adiabatic processes, there was 0 heat transferred. But for isochoric process, there is heat transferred. So let me write those down. We're going to need them for comparison. The heat input is the sum of the heat transfers from A to B and B to C, which is the same term as the one you see in Carnot cycle, and an additional term that comes from our isochoric path. And let me write down the heat output, making sure I'm writing it down as a positive quantity. And once again, it has the same term as the Carnot cycle and an additional term that comes from the isochoric path. Alright, so these are our results that we'll use for comparison in our summary video. Oh, I forgot one thing. Those pressures, they are not given, but they can be determined from what's given. Let me just write them down. For all of them, we have the temperature and volume at those points. So it's a matter of using the ideal gas law to write down what the pressure is in terms of those. So I guess I need pressure at all 4 points. Pressure at point A, point B, point C, and finally point D. Alright, so when it comes to comparison, we'll just use these to work out pressures numerically rather than working out the algebra, because once again, there's no real payoff here. The expressions don't simplify. Alright, so that's everything, and I guess the next video should be the summary video. We'll put all this together in the summary video and kind of see what we can take away from comparing these 4 realistic heat engine cycles. Until then, bye. Hi, we've been looking at heat engine cycles, and in this summary video, we'll compare the 4 heat engine cycles that we have analyzed so far. Those 4 cycles we analyzed were Carnot cycle, Otto cycle, diesel cycle, and Stirling cycle. So that you have it all on one page, let me briefly describe the processes that are involved in each cycle. Here's the PV diagram for the Carnot cycle. So in Carnot cycle, starting from high pressure, low volume, the gas first undergoes isothermal expansion. Then at some point, the expansion continues adiabatically. Then the gas is now contracted isothermally. And at the right point, the gas continues compression adiabatically with increasing temperature that eventually reaches the initial starting point. The isothermal process happens along an isotherm, indicating all the different pressures and volumes with the same temperature. And while the gas changes temperature, the heat exchange with the surrounding is zero because it's adiabatic. The Otto cycle is one of the 2 internal combustion engine cycles, and here's the PV diagram for the Otto cycle. We can start from high pressure, low volume state. At this point, the ignition of the fuel-air mixture occurs. Then the pressure of the gas increases very quickly, so that there's no time for volume to change. And once the pressure is at maximum, then the gas expands adiabatically, pushing out the piston in what's sometimes called power stroke. At the end of the stroke, we idealize it as undergoing isochoric cooling process to release waste heat to the surrounding, and to return the engine to the original system, it is adiabatically compressed to return the point where the fuel and air mixture was originally ignited. Somewhere along the process, having expelled the exhaust, taken in new oxygen-rich air, and mixed in the fuel. I should note that these 2 curves are adiabatic, and since it's adiabatic, the temperatures vary throughout the whole process. There's no isothermal process here. The diesel cycle is the second of the internal combustion engine cycles, and here's the PV diagram for the diesel cycle. So let's start at the state of the engine where it's at high pressure and low volume. It's at a very high temperature. Fuel is injected that ignites, causing the gas to expand isobarically. And that's the idealization. At some point, the expansion continues adiabatically. And at the end of the expansion cycle, the gas undergoes cooling. We idealize it as isochoric cooling. And to return the engine to the original point, it undergoes adiabatic compression where the temperature of the air rises until it's at a point where fuel is ready to be injected, igniting all at once. The isobaric and isochoric processes are clear, and these curves are adiabatic curves. There's a reason all these curves in the internal combustion engine are adiabatic. In an internal combustion engine, there's no real thermal reservoir. The source of heat is the ignition of the fuel-air mixture within the engine. And expelling the waste heat happens by, well, expelling the gas and taking in new air. Okay, the last of the cycles is the Stirling engine cycle, which is unique in that it is a real engine cycle, unlike a Carnot cycle, and also it is not an internal combustion engine. Heat is provided externally. You can see that in the engine cycle processes. We'll see. So here the best place to start would be the low pressure, low volume state of the engine. And from this state, the engine is in contact with a high temperature reservoir and absorbs its heat isochorically. And once it reaches the highest pressure, and then the engine starts to expand. And this we model as isothermal. This is possible because the Stirling engine is in continuous thermal contact with the thermal reservoir. At the end of the expansion cycle, the engine is designed so that the gas is now in contact with the low temperature reservoir, so it undergoes cooling. We idealize it as isochoric cooling. And now, to reach the original starting point, the gas remains in contact with the low temperature reservoir, and heat is being removed from the gas as it's compressed. So, like with the Carnot cycle, with the Stirling cycle, the upper and lower curves are on two different isotherms. And the distinction from the Carnot cycle would be, whereas in the Carnot cycle, these two isothermal curves are connected by adiabatic curves. In a Stirling cycle, they are connected by isochoric curves. Alright, so the point of this summary video is to compare the cycles. So we've been using consistent labels for all four cycles so that we can compare them. They are best labeled on the Otto cycle. So we use the high volume and the low volume endpoints, and this ratio of the volumes is going to be important. And we use as parameter the highest temperature within the heat engine cycle that occurs on the Otto cycle at this vertex, and the lowest temperature on the cycle that happens at this vertex for the Otto cycle. That's it. Let me label all the other diagrams so that they all have these four parameters, which we are going to set common between the four cycles so that we can compare them on a similar footing. Same thing for the Stirling cycle. Now with the Stirling cycle, it's special that the entire upper curve is at the high temperature and the entire lower curve is at the lower temperature. With the Carnot cycle, I have to be a little bit careful because looking back at my note, the way the volumes were labeled was rather than using the highest volume in the cycle, I used the volume after the initial isothermal expansion. It doesn't make a real difference in one quantity we care about, and the difference it makes on the other quantities are rather negligible. Alright, so we need to set some of these parameters. I looked them up, and what I see is for Otto cycle, the typical compression ratio is 10. In other words, VH is approximately equal to 10 times VL. Alright, we'll use that. And the second easier thing is the low temperature. We can just assume that the heat is being expelled into the regular surrounding, so room temperature, about 300 Kelvin. Now the biggest thing is the high temperature. I wasn't quite sure what's the right temperature. So I looked up Wikipedia page for something called adiabatic flame temperature. This is the Wikipedia page for adiabatic flame temperature. It's the maximum temperature of flame of some fuel and the air mixture can occur. So for the mixture of gasoline and air, this says that the adiabatic temperature is about 2100 degrees C. Or in Kelvin, this would be about, let's say, 2400 Kelvin or so. But let me use a slightly lower temperature. Let's say 1500 Kelvin. Either way, it doesn't matter a lot for the point I'm trying to illustrate, but 1500 Kelvin sounds more reasonable, so let's use that. So I'm going to label the TH, high temperature, as 1500 Kelvin. Alright, so that's all the parameters. We already labeled the other diagrams. So let me write down these parameters on this corner as a reminder for myself. The high temperature is 1500 Kelvin. The low temperature is at room temperature, or 300 Kelvin. And we'll say high volume is 10 liters, or about 0.01 cubic meter. And the low volume is about 1 liter, or 0.001 cubic meter. By the way, I don't know if these are reasonable parameters for an automobile engine. I'm just, they're probably reasonable within a factor of 10 or 100. Alright, so there's one more parameter we need to nail down, and that would be the number of gas molecules. It affects what the pressure is and so on. I think a good value will be this. We'll set number of molecules such that when you multiply it with the Boltzmann constant, that this is equal to 3 joule per Kelvin. I think this number has an upside of making sure that the low temperature point is at approximately 1 atmosphere. So we derived the formulas in previous videos where we can just plug in these numbers to get the net work done, heat input and the heat output. So let's go do that. The first cycle to look at is the Carnot cycle. So all these expressions for work done, heat input and heat output seem to be, in terms of parameters, we already have numerical value of. So let's plug them in and see what we get. First, QH. Plugging these numbers into my calculator, NK, 3, times the high temperature, 1500 Kelvin, and the natural log of the ratio of the volumes, so that would be 10. This is what I see when I plug in these numbers into calculator. It's 10,361.6 joules, or rounding it 10,400 joules. Let's keep going. QL. Plug in these numbers into calculator, that is with the substitution of TL for TH. We get 2072.33 joules, or rounding it about 2070 joules. So finally the work done is the difference between them, but I can also just plug in numbers into this equation. And when you plug in the numbers, this is what you get. The work done is 8289 joules. Now, if energy is conserved, then the sum of these two quantities, the rejected heat and work done, this is equal to the heat transfer at the higher temperature. 2070 plus 8289 is approximately 10,400, give or take 100. Let me copy these numbers over to the summary page. I will round them to the 100th place. So the heat transfer then work done for Carnot cycle are, and here is a useful quantity we can define called efficiency that we'll talk about more next week. For now, I will say we define efficiency as work done divided by heat input. So in the case of the Carnot cycle, the efficiency is 0.8 or 80%. Now, because this is actually an unrealistic high number, I need to point out that this is really high temperature, 1500 Kelvin. It's high enough that if a piece of metal were at that temperature, it'd be glowing white hot. But that is the efficiency we have for such a high temperature. Alright, let's move on to the Otto cycle. So there are a lot of numbers here. We need to calculate them out first. So let me make some space. First, we are going to calculate all those intermediate numbers that we need. Pressure at B and pressure at D. So plugging the numbers for the temperature, NK, and the volume, I get, using my calculator, PB is 4.5 times 10 to the 6 pascals, or about 45 atmosphere. And PD is 9 times 10 to the 4 Pascal, or about 1 atmosphere, as was our design. Let's keep going. We need the temperatures, TC and TA, and plugging all the numbers, TH, VL, VH, and the gamma for monatomic gas. We get for TC 323 Kelvin, and we get for TA 1392 Kelvin. Temperature at point A is pretty close to the highest temperature, the 1500 Kelvin. We need two more pressure numbers, PA and PC. So PA is NK times TL times volume at high volume raised to the factor of gamma minus 1 divided by VL raised to the factor of gamma. Putting that into my calculator, I get PA is equal to 4.18 times 10 to 6 pascals, and PC is equal to 9.695 times 10 to 4 Pascal. I don't know if I needed to keep that many significant figures. Alright, so we have all the numbers we need. Plugging these numbers in gives us our result. Let's calculate the network first. That seems easier. Also, it's the first line. So plugging in 3/2 NK times TH plus TL and the two temperatures we now calculated, TA and TC, we get 380 joules. It's a much less amount of work than what I saw with the Carnot cycle. Let's keep going. The QH, plugging in the PB and PA that we calculated, we get 484 joules. So heat input is also small. I guess I can kind of figure why. So with the Otto cycle, the only heat transfer happens along AB and CD. Whereas with the Carnot cycle, the heat transfer was occurring throughout the isothermal process. Let's plug in the numbers to QL. Oops, I think I made a sign error there. It should be PC minus PD. So let me do that. And the number I get is 104 joules. Alright, and they all seem to check out. When you add QL to the work done, you do get the heat input to the system. Let me copy this over to the summary page. So for the Otto cycle, QH is 484 joules. The work done is 380 joules. And the heat exhaust is 104 joules. We can calculate efficiency as before, and it's 78%. That's interesting. So it's not too far from the efficiency of the Carnot cycle, but it is less. And that's going to be important as we go. We'll see. Alright, let's look at the diesel cycle. There are a lot of numbers we need to calculate, so let me make some space here. The preliminary numbers first. So TA is plugging in TL and VH, VL, and gamma, 1392 Kelvin. So like with the Otto cycle, this is pretty close to the highest temperature of the heat engine cycle. And using this number, I can calculate PA, which is 4.18 times 10 to the 6 Pascal. And we can calculate VB, which is not much more than a liter, what we started out with. It's 1.077 liters, or times 10 to minus 3 cubic meter. TC is plugging in all these numbers, we get 340 Kelvin. So this is all the numbers we need to calculate the heat transfers and the work done. Let's just go down the screen. Let me free up some space. So the heat input is plugging in all these numbers, 3/2 NK times the difference of the temperatures, plus PA times the difference of the volumes. I get 806 joules. It's also small like the Otto cycle, so I think the same reason applies. Let's calculate QL, the heat output of the heat engine. That's equal to 178 joules. So the network should be difference between them, but let me plug in these numbers into my calculator to just double check. And I get 628 joules. That seems reasonable. Let me copy those to the summary page. So for the diesel cycle with these parameters for one loop, QH is 806 joules and QL is 178 joules. And the difference between them is work done, or work done is, I can also copy from the other page, 628 joules. Alright, somehow heat input is larger for the diesel cycle.
And you could credit the isobaric expansion for that. The isobaric expansion does require a lot of heat.
Alright, let's calculate the efficiency as before. And the efficiency is again about 78%. Now, once again, a reminder, these numbers are based on fairly high temperatures. And when you are actually designing these engines, real world considerations come into play. For example, for an Otto cycle, until it reaches this point here, the engine cannot reach temperatures where the fuel-air mixture will just ignite on its own. That leads to something called knocking. With the diesel engine, the design is different. The fuel gets injected at that point, so there's no real limit to how much you can compress the air, and the compression ratio does end up improving the efficiency of the engine. Alright, so we have one more left, the Stirling engine cycle. Once again, we have a lot of the numbers that we need to work out first, so let me make some space for them. So we need to work out all those pressures. Pressure at point A is 900,000 Pascal, or 9 times 10 to the 5 Pascal, or about 9 atmosphere. Pressure at point B is even higher, 4.5 times 10 to 6 Pascal. But it's comparable to what we have seen before, which makes sense since we are using the same temperature and volumes. After isothermal expansion to point C, it reaches the pressure of 450,000 pascals, or 4.5 times 10 to the 5 pascals. Pressure at point D should be close to an atmosphere, and it is. It's 9 times 10 to the 4 Pascal. So with these four numbers and the parameters we picked earlier to define this system, we can calculate all the heat flows and the work done using the heat flow. So let's write down the heat flow first. I'm using this complicated expression here, but where I do know all the numbers, so it's a matter of putting into my calculator. And the result is 15,800 joules. That seems larger than before. Let's keep going. The heat output from the engine is 7,500 joules. And the work done is, plugging in all the known numbers into the formula for network, we have 8,300 joules per cycle. Alright, everything seems to check out. When you add QL and W, you get QH. So let me copy this over to the summary page. So the heat input at the high temperature limit is 15,800 joules. And the work done is, rounding it up, 7,500 joules. Alright, the last quantity, QL, the heat outflow into the environment, is 8,300 joules. Let's define the efficiency as before, which is 53%. So there's some picture that's emerging in this comparison here. So those are the numbers. I want you to pay particular attention to these, the efficiency numbers. as you look at them, what I'm hoping you will glean is that there's a pattern here. The efficiency for the Carnot cycle is greater than the efficiency for any of the other cycles. We'll talk about this more in chapter 4, but Carnot cycle is the ideal heat engine cycle in the sense that given any two extreme operating temperatures, it's the Carnot cycle that's going to give you the highest possible efficiency. You can kind of figure out why that's the case by looking at the Stirling cycle, where the efficiency is much lower. But Stirling cycle is so much similar to Carnot cycle. In fact, even the amount of work done is very similar. They're both quite large. But the reason Stirling cycle is so much less efficient is because there's more heat input. With the Carnot cycle, these two isothermal curves were connected by adiabatic curves. So there was no heat input then. But with the Stirling cycle, it's not adiabatic, it's isochoric. So there is a heat input there. And that's what's reducing the efficiency of a Stirling engine. Although this number actually is more realistic, except because of the operation of Stirling engine, it cannot run at 1500 Kelvin. A more likely temperature for Stirling engine would be something like 700 Kelvin. So with the Otto and diesel cycle, what's more wasteful here compared to the Carnot cycle is that even though this is the highest operating temperature, not all heat input is at this temperature. At this point, it actually starts out at temperature of something close to, I think, 1300 Kelvin. So some heat input occurs at lower temperature, and that's ultimately going to be what's responsible for this lower efficiency. And it's the same deal for the diesel cycle. Alright, I think that's enough foreshadowing. For now, what I want you to pay attention to is that the Carnot efficiency is the highest efficiency. So if we just want to estimate efficiency of a heat engine, and let's say as a matter of bare minimum of parameters, we know the operating temperatures, then we can estimate the maximum possible efficiency by using the Carnot efficiency. And pretty soon you will see the formula for the Carnot efficiency, which is actually much simpler than Otto, diesel, or Stirling cycle efficiencies. Alright, so until next lecture, bye.